Okay, today we're going to discuss another type of random walking. It's called walking for a reason. Um, Actually, it's not random walking anymore, right? It's just a walking. And walking for a reason, this reason usually you can consider it as food or a resource or target, right? So foraging and searching behavior from animals, right, from human beings, um, they can be addressed by this type of model, walking for a reason. And the spatial pattern of walking for a reason depends on the structure of the environment, of course, because you are walking, you are searching for resources. So how these resources are distributed matters, right? Where are the resources? And how does the environment influence mobility? Are you considering that this walker has totally free movement, or there are some obstacles in this environment that this walker needs to avoid when it tries to find resources? And also, walking for a reason behavior is affected or depends on the individual motivations or strategies. Is this for a walker following optimizing strategy, which means perfectly rational, perfect information, wants the best choice, or it can only follow a satisfying strategy, which means that there is limited information and it can only get what he can, not the best. Okay, only good enough reasoning. And in 1956, Herbert Simon, he proposed a very simple model for walking with a reason. Let's say it. A simple model of satisficing based foraging, and you can find this literature in Canvas. Okay, this literature is there in Canvas. So what is the principles? What are the principles of this model? Walkers searches for targets on a lattice with an energy level of E. And each walker can move in one of 4 cardinal directions. Okay, and there is a vision defined for the walker. Okay, vision is detection radius. If the target or the food or the resource is within this radius, walker moves towards it where shortest path, which means that after each step, if this walker found a target within its vision, it will go directly to that specific cell to get the resource, to get the target. And collects energy at each target, and energy is recharged to E, which means that if a target is found, the walker will go directly to that target, right? And after that, it will collect the target and recharge its energy to max level, which is E. It also means that each step also costs energy of the walker. Okay, so the walker dies if energy falls to 0. Let's just assume that for each step, 1 unit energy will be consumed. Okay, when you move each 1 step, 1 unit energy is consumed. Okay, also there is another parameter called p direction change. It is the probability of changing direction at each step, which means that if this p direction change equals 0, that if that's the case, if it is equal to 0, the walker will go along a straight line because the probability of changing direction is 0. Okay, if you set this value to 1, it means that at each step, the walker will change direction. Of course, you can make it random, right? You can choose a random direction from north, south, west, and east, but there will be a change of direction if you set this parameter to 1. Okay, so here we have the rules for this model. Okay, and critical parameters. Okay, the first one is about the environment, proportion of lattice with resources, PR. For example, your lattice is 9 by 9, which means there are 81 cells. And if the PR is equal to, say, 10%, which means that 10% of 81 cells have resources. The rest 90% of the lattice does not have resources. Okay, and the maximum or start energy level is E. We have talked about this. This is the max energy level that the walker has. At each step, 1 unit will be consumed. 1 unit will be consumed. And also, we need to define a vision, which is V. So here is an example. Here is an example of lattice with resources. So currently, this walker is at this specific location with a black dot. Okay, the vision of this walker is set to 3, which means when it is standing at this specific location, it can discover all the cells 3 units away from it. And here we have a dash line, right? It means that this walker now is moving from this current location to the location indicated by this triangle. And all these empty circles, they are the cells that this walker can see from this location with a triangle. Why? Because the vision of the walker is 3. If the walker is standing here, it can say 1, 2, 3, 3 units away. 1, 2, 3, 3 units away, or it can say 3 cells away. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. Anyway, the vision is 3, and this empty circles, they are representing cells that can be found, can be discovered by the walker when the walker is standing at this location indicated by this triangle. Okay, so new locations variable at each new step is equal to 2 times of V plus 1 if the walker is moving forward, which means there is no change of direction. So from this black dot to this triangle, 1 step was taken. And how many new sites can be seen by this walker? 1, 2, 3, 4, 5, 6, 7. 7 new sites. And the V is equal to 3. So 2 multiply 3 plus 1 is 7. And you need to know that when new sites are discovered, the walker will also have the information about resources on these new sites, which means that if 1 or more new sites have resources, have food on them, the walker will know. Okay, so for this specific example, currently the walker is standing here at this black point, right? After next step, it will be at this location indicated by this black arrow, by this black triangle, and he will know if there is food or resources at any of these newly discovered locations, newly discovered cells. Okay, and if there is food on one of them, it will go directly to that cell to get the food and recharge its energy level to E. But you should know that it will also consume energy during moving. No matter this moving is only for searching for new cells, or this moving is for this walker to go to that cell for food. Okay. Anytime if there is a movement, there is energy consumption. And if the energy is equal to 0, drops to 0, the walker will die. Okay, this is a moving forward situation. On the other hand, if currently this walker is at this location with black dot, and if it changes direction to the right or to the left, you can say that only v plus 1 new sites can be seen. Okay, which is 4 here because v is equal to 3, right? So if you compare these two examples of movement, which one is with higher efficiency in terms of finding new sites or finding food? Because more new sites means higher probability to find food, right? Obviously, the top one, which means that turning to another direction is a relatively worse decision to make. It's better to just follow a specific direction and find new sites at each step. And after each step, 2 times of v plus 1 new sites will be found if you keep moving forward. Okay, so of course, this one is better. This one is better. And okay, let's do some analysis of this very simple foraging model. So probabilities of finding a resource or target is following something called geometric distribution. Okay, so this is a conclusion. But what is geometric distribution? If you have ever enrolled a statistics class, you should have learned this distribution before because it's very basic. But let me just review it and explain it here, okay? So geometric distribution is a probability distribution of the number of Bernoulli trials needed to get a success, okay? And what is Bernoulli trial? Bernoulli trial, or it is called binomial trial, is a random experiment with exactly 2 possible outcomes, success or failure. Okay, it has a binary outcome, success or failure. So for example, we have a group of 100 people. 20 of them have geographic background. So P is equal to 0.2. Okay, and then we randomly pick one from the 100 people and call it a success only if the picked one has geographic background. So what's the probability of a success? 0.2, because 20 out of 100 of them have geographic background. So the successful possibility, the probability for success is 0.2. Otherwise, which means the picked one has no geographic background, we call it a failure. Okay, so 100 people, 20 of them have geographic background. Okay, you pick one of them and say if it is a success or a failure. Okay, when you find out it is a success or a failure, then you just finished a Bernoulli trial. Okay, so what we care is this question. What is the probability of getting the first success at the X peak? Because when we finish one Bernoulli trial, it could be success, could be a failure. And we repeat this trial many times until there is the first success. And what is the probability of getting the first success at the X peak, right? So we for example, we just finished the first peak. It was a failure. Okay, then we repeat this. It's the second success. It's the second peak. And the second peak is still a failure. Then we repeat it. It's the third peak. And after the third peak, we have a person with geographic background. Then we say that we have a success. We have the first success at the third peak. At the third peak. Okay, so this is Bernoulli trial. So the probability distribution of the number X of Bernoulli trials needed to get one success. Okay, so the example I used in the last slide, the p-value was equal to 0.2, right? So let's focus on this curve with yellow dots. Okay. The probability of having the first success after the first peak is 0.2. Okay, and for different X value, you can say the probability drops. And if your successful probability, if your probability of getting a success is pretty high, is 0.8, it means that there is a probability of 80% that you will have this success. You have this first success after the first peak. That's why this blue dot is right here, and its what? Its y value. Its p-value is equal to 0.8. One x value is equal to 1. 1 is right here. Okay, so this is Bernoulli trial, and since we know that this working with a reason is following geometric distribution, we can do some mathematics to quantify this walking, different parameters in this walking, following geometric distribution. So let's just define probability that no newly visible set contains a target is rho. Rho is equal to the difference between 1 and PR to the power of the mean value of V. Okay, PR here is a proportion of lattice with resources. We defined this before, right? This triangle bracket here, this pair of triangle brackets means mean value. Okay, mean value V is the mean of newly visible sites after each step, which can be simply considered equal to V. V is the vision of the walker, right? So here, 4.12 is the equation to find out the probability that no food can be found among newly seen cells. Okay, that's rho. Secondly, probability that target will be found on the case move. Okay, since the failure probability, the probability of failure is rho, it means that if we success at case step, the previous k minus steps, they were all failures. That's the reason why we have mu to the power of k minus 1 here. Multiply the last step. It's a success because we found the food, we found the target on the case step. So for case step, it is 1 minus mu. Sorry, 1 minus rho, because rho is what? Is no food, no target. 1 minus it is what? Is the probability of success. Okay, so that's PK. Okay, let's continue. Next one is important. Expected number of moves or search time to find a target, to find food. Okay, so the equation is here, and you can find more steps of this calculation in the literature I mentioned before. But let's just jump to the conclusion. M is equal to the reciprocal of the difference between 1 and rho. Rho is the probability of what? Of failure, right? Okay, so this is the expected number of moves to find food, to find a target, which is M. And eventually, we want to address the probability of death. Because like I said, at the very beginning, the walker has an energy level of E. And after each step, 1 unit of the energy will be consumed. If the walker cannot find food before the energy drops to 0, it will die. Okay, so death rate, probability of death is important. So probability of death is equal to the probability that the number of moves to find a target will exceed the difference between the starting energy and vision. So death rate, again, let's just jump to the result, is equal to rho to the power of E minus V. So this is death rate, or probability of death. That's more accurate. And the life expectancy of walker is the reciprocal of death probability. And the life expectancy of walker can also be considered as expected number of searches. What is a search? A search is a successful finding of food. For example, the walker is standing at a specific cell right now. And after the last step, there are some newly seen sites within your vision right now, right? And you just found that, the walker just found that one of the cells found after the previous step has food. So it will go directly to that location to get the food. Let's just assume that currently the walker has enough energy to get to the site, to the cell with the food, okay? And it gets there. Then this is a search. A search must contain a successful finding and getting of food. Okay, so that's called life expectancy of the walker. So we have so many formulas here, and let's use an example to get some feelings. Of these parameters. Okay, so for example, here we have a lattice with PR value of 0.001, which means that only 0.1% of the lattice have what? Have food, have resources, okay? So it's pretty hard to find a cell with food, I would say that, okay? Only 0.1% probability that the walker will find food. And the vision is 10. The starting energy is 100, okay? So according to 4.12, equation 4.12, the probability of not finding food is 0.009. Oh, sorry, 0.990. Sorry. Okay, according to equation 4.12. So that's the value for rho. Okay, and then according to equation 4.14, what's the expected steps to find food? Which means to finish a search, it is 100 steps. Okay, it means that usually, given this PR value and vision, you are expected to move 100 steps to finally find food. Okay, that's M. M is important. And let's just continue. What's the death rate according to E, V, and rho given here? The death rate is 0.405 according to what? According to equation 4.15. What does it mean? It means that during a search, during a search for food, the probability of death during a search is 0.405. If we calculate the reciprocal of P death, or P, it is equal to 2.46. which means the life expectancy of this walker is 2.46. What does it mean? It means that you can expect for each walker, it can survive 2 searches, which means it will successfully find food 2 times on this lattice. And on the third search, on the third trying to find food, it will probably die because the life expectancy is only 2.46. It is smaller than 3. It means that, okay, given this PR value, given the vision, given the starting energy of the walker, it will survive 2 searches, which means it will find food 2 times before dying. But it will probably die. It's very likely for it to die during the third search. It will probably not find the food for the third time. So it means that, okay, this is not a long-living. This is not a long-living walker. Okay, if that is the case, I would say it's a very harsh environment to survive, and the walker itself is not strong enough because the starting energy decides how long it can go before the death. Okay, so energy here, starting energy here is very important. So what if E is much larger than the expected number of moves, or is much larger than M? Okay, so M here is 100 and E is also 100. They're equal to each other. What if E is equal to 1000? And you do this calculations again, and you will see that if E is equal to 1000 and the rest parameters in the example above stay the same, the life expectancy is 20,000, which means that what? This walker can survive 20,000 searches before going to die, before the death, before death. So you can say here, in nature environment, I don't think any species, of course, human can do that, except human. No species can change the environment. What they can do is adapt to the environment and try to find the food, which means that the value of PR cannot be changed for most species. Human can change that, right? We can grow food. We have supermarket. Of course, PR for human is not this small value, but for most animals, they have no choice. The environment is there. You are in this environment. Okay, go survive. Okay, PR cannot be changed. But after generations of evolution, the value of E can be changed, which means the ability of storing energy is something animals can evolve and can try to enlarge it. So if your capacity for energy changed from 100 to 1000, you can survive much longer, much longer. Okay, so now you get the feelings of this. Or you can say here we have a direct impression of the meanings of these parameters, PR, right? If it decides if the environment is abundant with resources. V is the vision of the worker. It is decided by the worker itself. Okay, it is also a very good indicator to address the ability of that animal or that individual to find food. The larger the vision, the more new sites you will find after each step. Obviously, the larger the V value, the stronger ability that individual has for searching food. Starting energy is also important. It decides it decides the size of your backpack. right? You have this backpack with food, full of food, and you can only find another site with food to refill your backpack before your backpack is empty, right? Obviously, the larger the better. If we do not consider your ability to carry the bag, okay, the larger the bag, the better, the longer you will survive. That is E, starting energy of this individual. Okay, so you can say that for most species, for most animals, PR is not something they can change. They can change V, they can change E. Okay, so of course you can play with these formulas a little bit, change some values of them, and say what's the difference of outcomes. Okay, and here now we have a model. We have a model from the textbook. You can play with it a little bit. Okay, and now let's ask this question: how does the walk affect the success probabilities? Okay, of course, the vision is important, right? I mentioned it before. The larger your vision is, the more new sites you can find after each step, which means that your efficiency increases dramatically when your vision increases. Okay, and also the directional persistence uh, affects the success probabilities. Do you still remember these two figures here? Well, yeah. Obviously, following a specific direction permanently or long time, just go along a specific direction, is a better strategy than changing direction frequently. Again, it's about efficiency. If you go along a specific direction consistently, you will find more sites after each step compared to turning to another direction, right? So directional persistence is also important. And in the model, we can assign possibility of direction change at each step. Of course, if you want this searching to be very efficient, you can assign a very huge value, a large value to directional persistence. For example, 0.99 is almost a straight line. Of course, if you give 1 as a directional persistence, it means that what? Oh, sorry. If you give 1 to the model and make it the probability of direction change at each step, it means that the efficiency of the walker will be extremely low, because at each step it will have to change direction because the probability is 1, right? If you gave a specific value that is very low to the walker, for example 0.0, which means no direction change at all after each step, it means that this walker will just go along a straight line, right? And also another factor here is called self-avoidance. Do not visit locations have been visited before. If you turn this on, the efficiency of the walker will be pretty high compared to those walkers with this switch off. If you turn this off, it means that the walker could just go back to a cell that has been visited before. Since it has been visited, if there was food, it has been collected. If there was no food, then you go back to it. It's meaningless, right? So self-avoidance can increase the efficiency of the walker dramatically. Okay. And yeah, this specific model is 4.4 Manhattan sausages dot n logo. I will tell you the reason why this name here is very strange. It's called Manhattan sausages. Okay, so this is a model. Okay, let's say say the influence of term probability on mean sites searched per step. Okay, like I said, term probability can be from 0 to 1. If it is 0, it means that the walker will go along a straight line. If it is 1, it means that at each step, the walker will change direction. Okay, here we have some special patterns as examples. If P is equal to 0.05, which means the term probability is pretty low, you can say the spatial pattern of the trajectory of the walker is very simple, several straight lines, because it's not likely to change direction. But if you increase the p-value from 0.05 to 0.3, 0.5, 0.75 to 1.0, you can say the area covered by the trajectory of the walker decreases dramatically. So here we have a large area, shaded area, gray area here, that is covered by the walker, okay, after a specific number of steps. But with the same number of steps, the walker can only cover this small area of gray if the p-value is equal to 1.0. And if I'm asking you to find food, which p-value you want to use? This one or this one? Obviously, this one, the lower one, because you want to cover as large area as possible to find more food to survive. Okay, so we have a lot of box plots here to show you the mean size searched per step. Obviously, when the p-value is equal to 0, okay, we have the largest number for mean size searched per step. Okay, and this value drops accordingly when the p-value increases, when the term probability increases. Okay, so foraging behavior. On the left side, we have high efficiency searchings, or you can say searchings with high efficiency. And on the right side, if you turn your direction frequently, your searching efficiency is low. Okay. And Wiener sausages, or Manhattan sausages. Okay, it was proposed by Norbert Wiener. Okay, a neighborhood of the trace of a Brownian motion up to a time t. Okay, and generated by taking all points with a mixed distance of Brownian motion. So here we have a new term. It's called Brownian motion. Brownian motion is something you can use to address the random movement of particles suspending in liquid or suspending in air in the space. Okay, so you can consider that within your room there are a lot of particles suspending, and there are collisions, and they are all randomly moving within this space. Okay, so Wiener sausage is what? Is a sausage with a specific radius. You can hear here is you can see here is a Wiener sausage in 3 dimensions. So we can, if we collect all those trajectories of particles, right, and we project this 3D trajectory to a 2D surface, you should have a sausage shape, how can I say, sausage shaped polygon. See that, right? Because this projection is a projection of the trajectories of these particles, and only particles they are close enough to each other are visualized here. Okay, which means if you project these trajectories to this surface, you will have a 2D sausage with a specific radius, and the central line of this sausage can be considered as a what? As a trajectory of Brownian motion. because actually the sausage is formed by all those particles following or doing Brownian motion in this 3D space. And this Wiener sausage model can also be used to address animals' foraging behavior. Okay, so what's the implication of this model, Wiener sausage? Ballistic motion or straight line motion to random walk behavior. If you change your moving strategy from straight line movement to random walk movement, your effectivation falls from approximately from 2V to half V. Right? I showed you two examples of new sites that can be found after each step if that step is moving forward, which means keeps the same direction or turning to another direction. Effectivation is another word for the number of new sites after each step. Okay, the number of new sites you can say after each step. So if the energy is 500, life expectancy falls from this huge number 18,122 to 11.6. It means that if you change from straight line movement to random walk movement, animal requires 4 times as much energy storage to survive. Which means that the highest, I mean, the searching behavior, the foraging behavior with the highest efficiency is what? Is straight line searching. Okay, clearly a more efficient search strategy is beneficial, which means that if you are following a straight line, you're following the same direction to find food. Okay, it's more efficient. You can survive longer. You can find more food before your energy. Or you can say this, it's more likely to find food to recharge your energy before you die, before the walker dies. Okay, so although you cannot teach animals and tell them how to change their strategy, but there is you cannot do that, but there is something called natural selection. Okay, after generations of evolution, animals, they know how to do this with efficiency. Okay, this is a relatively longer video and I'll just stop here. Okay, thank you.